This is a map of Dallas, Texas, and each red dot you see here is the GPS coordinates of a smart meter that I received while driving down the freeway with a software-defined radio in my car. The height above the ground of the red dots represents how long they've been running since they last had a power outage. This information is transmitted in the clear. This one you can see here is 1767 days, and this talk will be about how I receive this information using my software-defined radio. I'm Hash. I'm a reverse engineer by hobby. I don't do this professionally at all. I just, in my free time, like to reverse engineer things. I'll be talking specifically about these meters made by Landis and Gear and used by the power company Encore here in Dallas. I don't do that to name and shame any companies, but the information you'll see is very specific to how they've set it up and how these devices work. And so doing this reverse engineering work, smart meters are kind of a contentious thing. Infrastructure is kind of contentious to work on. And there was a good talk by Travis Goodspeed where he recommended instead of hacking infrastructure, look at the devices that use similar parts, similar microchips, and reverse engineer those instead so you don't attract a lot of attention. But recently, there's been a lot of ransomware activity and other things like that. And I feel like ignoring these devices and not touching them for fear of any kind of repercussions is the wrong way to go about it. If there's low-hanging fruit out there, if there's challenges with these networks, we need to look at it and understand if technology is advanced to a point where anybody can do this. And so using this marketing video produced by Landis and Gear, I'll give you an overview of how a smart meter network works. So on the side of any home, business, anywhere else, in order to get power and measure it, they need to have a meter. It used to be the old meters with the little spinning wheels you would see on it, but now they've advanced and they have radio frequency circuitry in there and they have microcontrollers and things that log that information and transmit it back wirelessly to the power company. But they don't just broadcast it all directly back to the power company. These meters actually form a giant mesh network. And so what that means is that each meter broadcasts their message and it's relayed across town to wherever there's a collector or a router on a pole, and it aggregates that information. And so it's receiving all this data from these meters that are hopping across the network. It gathers it up and either it has a cellular modem in it or it relays it back to a substation that you can see if you're driving down the road anywhere and you go by one of these kind of power station looking things, you'll see a pole in there and there'll be some antennas on it, like this one that's shown right here. And so inside there, it aggregates that data and then it carries it back across your traditional network, whether that's a cellular modem or a wired connection to an operations center. And so there's not a lot of information that's published about these things. As you can imagine, they're pretty quiet. But there was a paper that was written by some of the engineers that work for Landis and Gear, and it was available on the IEEE. And so I paid a small fee and I got this paper and I read it, and it was based on a system that was deployed here in Dallas, funny enough. So you can see maps of Dallas in there where they were showing how they were testing this system. And one incredibly interesting part was this piece. They talk about a geographical routing protocol, something I had never heard before. And it basically says that they employ a routing scheme which utilizes the geographical coordinates, the latitude and longitude of the communicating nodes being smart meters. And I thought, I got to take these things apart. Like, how can I get one of these? So I headed over to eBay because I can't exactly pull the one off the side of my house. But sure enough, these things are for sale all over the place. I don't have any idea why they're for sale on eBay, but that's neither here nor there. I just started buying them a couple years ago and buy one here, buy one there, find a good deal on it, and find any other infrastructure pieces that said Landis and Gear on them. And so this is my office here, the side you can't see, and my workbench. And you can see I've got a lot of smart meters. It's comical at this point, I would say, when you walk around my house or my garage. I have circuit boards everywhere from smart meters, smart meter modems, and all these different things that I started to analyze and take apart and try to figure out, how does this network work? There's just nothing that's published about it. So I started hooking up to the microcontrollers and looking at the circuit boards and trying to figure out what are all the parts that are on it, and set up a software-defined radio receiver here that you see on the screen. And it's just grabbing packets of information that are being transmitted around me and saving them to a file. And I just kind of stare at those packets and stare at them to try to figure out what is going on with this thing and how do they work. And so even more modems, and that white device there is a collector, like you saw on a pole that I got lucky and found on eBay. And then behind me, you see over my shoulder here is a Faraday cage. And this allows me to put devices inside there and isolate them so that they can't transmit anywhere else except for inside this box right here, so that I can work on them and see what they're doing. And so I began by creating schematics. And so these were all created by me by looking at the circuit boards and figuring out what parts are on there and how do they work and how are they wired up so that I can just start to dive in further and further and figure out what they're doing. And so this is the transmitter chip that's used. Now, inside of them, in the very back, is basically a massive switch. This switch can control or turn on and off 48,000 watts. So essentially your entire house. And inside the meter, they can send a message wirelessly to turn your power on or off. So if you move into a new place and you call the power company and say, hey, I want to start service, they can send a message right down and this thing clicks right open or clicks closed. If you didn't pay your bill, it goes the other way and they can turn the power off. And it can do this 10,000 times according to their spec sheet. So it's not a one or two kind of time thing. They can just turn power on or off anytime to start and stop service. And I thought, well, what if somebody else could send a signal that could turn this thing on or off? And how would that be done? And how protected is this this network that they talk about? And who's looking at it? And so I figured, why not me? And so I started diving in and analyzing these things. And so the firmware that I managed to dump off of one of these meters microcontrollers, basically the software that's running inside there, I loaded into this software. It's called Binary Ninja, and it lets you basically go instruction by instruction and try to figure out how it's working and document it. And so this is actually the bootloader for that chip. It's a much smaller file, and I started with it because, like I say, I do this on the side. And so, analyzing these things, there's a lot of data to go through, and it's tedious work. And so when I'm bored on the weekends, I pop this thing open and make a little progress here and there along my journey of reversing smart meters. This is a classic waterfall. What this shows is each one of these little spikes that you see popping up there is a burst of energy, a transmission from a smart meter. Almost all of these little peaky ones you see are smart meters, and you see they send data all the time. This is not once or twice a day or every few minutes. It's constant. And so I wanted to receive this data. And when I first started, I used this device here. It lets you listen to one channel. There's about 260 different channels that these meters hop around all the time. But this lets me listen to one. But it didn't really kind of scratch the itch of how I wanted to do this. What I wanted to use was this software. It's called GNU Radio. And what it lets you do is build radio receivers using software. And so what you see on the screen here is a bunch of little blocks that you put together, almost like Legos, like a really complicated Legos. And it will record, this will decode 10 channels worth of information out of the 260. And so I packaged this up into one smaller block and then stacked a bunch of those into another to try to receive. This one will do 240 channels at the same time. But this required a hell of a computer that I had to build, this matrix thing that's running behind me. And it worked, but not exactly how I needed. And so despair set in, and I started hopping on the internet, searching for some videos to try to figure out, is there another way to do this? And I happened across this guy's video. It's from Sandia Labs. His name's Jacob Gilbert, and they put together a package that can basically look at an entire spectrum, and regardless of where a transmission happens, it can tag it and send it out. So you don't have to listen to all 260 channels at the same time. You can just have this thing grabbing data, and anytime it sees any kind of data, it will package it up and hand it over to you. And so that's what all these blocks do. They look at bursts of energy, they pass it through on to the next block, they decode it. And so that allows me to basically listen to an entire smart meter network around me, whatever I can receive, and grab that data, not knowing what it is or the size or length of it or how fast it's being sent, but still decode it, package it up, and send it across. And down here at the bottom is where we start to get to the interesting part. So all that is kind of the plumbing. And when it gets down here to these blocks, what we start to do is really match on the data from the smart meter network. So the first block here, what it's going to do is look at the beginning burst of energy that's transmitted, these ones and zeros. And on my wiki, I documented everything about these smart meters and how they start. And so they start with this sync kind of word, they call it. So this information is the very beginning of a transmission. And so we match on that data. And once we do that, we get to the block that I wrote that's available on my GitHub. And this block specifically decodes transmissions from Landis and Gyr gridstream meters. And so what it lets you do is put in a CRC value. This is basically how they segment their networks. They give them each a different value here. And so two power companies can be right next to each other, and neither one of them will interfere by setting this value. So there's videos I have, other ones on YouTube, that talk about how to determine what that value is for your smart meter network if you're using the same meters. And then some other values I have there that let you filter by specific meter IDs and things like that. And so what we're looking to receive here is these packets. These are broadcasts that contain the GPS coordinates and the uptime. There's other packets like these D5 packets, and these are routed packets. So basically when it wants to carry data across a network from one meter to another, it crafts a packet like this. So the GPS coordinates are in these 5.5 packets. So what we're going to do is put these values in here, say we're going to run this flow graph, and all we want you to do is spit out every single meter ID you see. Every time it sends one of these transmissions, we want to dump it out to the screen here. And so you'll see it starts to grab transmissions just from a little antenna here in the office. They send out a lot of data all the time, and here it comes. So it's dumping out to the screen. But that in itself, I also feed out that data to a network port. And so with the Python script, we can connect to that network port and then do a little post-processing on this data so that we can see this information. And so what we'll dump out is the meter ID itself as the first value, then a uptime in seconds, that's that large value, then the 78 you see, which is the uptime in days, the latitude and longitude, like if you copy and paste that into Google Maps, it will just put a pin on a map of where that smart meter's location is, and then the current time that's stamped on it. And so I take this information, I output it to a spreadsheet, and I upload it to Google Earth. And using the KML format, it'll publish it in Google Earth and let you see it on the screen. And that was all those red dots that we saw in the beginning when the video opened up. We'll see them again right here in a moment. And so I take this, I copy paste it over and load it in. There's some work that's done to post-process it. I have it documented in another video. And so this was just a software-defined radio in my car driving down this freeway at 70 miles an hour. I wasn't going slow. I wasn't trying to do anything special. And these things are just bursting out energy all the time. But so far, everything I've done, it's all receiving. So the challenge is I can't actually talk back to this network that's around me because I don't own that network. I'm just listening to these clear text transmissions that they're sending out. But what would be real interesting is if I had a network of my own that I could experiment with. And so what I started to do was realize that perhaps I have enough stuff here that I've been acquiring over time to actually build my own smart meter network. And perhaps I've figured out enough of how they work with these different network IDs to do that. So I started tearing apart this collector that I had purchased. And I have a separate video online that goes into a little more detail about it. But there's a few key devices in here. These are all high resolution pictures that I post online on my wiki that shows all the parts that are in it. And so when I opened it up, I initially noticed a magnetic switch here. So if anybody opens one of these devices, it'll be notified. It has the ability to relay a message or something back to the power company, or maybe white security keys or something like that. They have a very large battery in them that you can see here, because if power goes out, they still need to be able to relay messages back. And power meters also have a way when power goes out that they can relay a few messages back to let the system know that power went out. This modem board, we saw some on my desk, but I use this in some other experiments later on. That is how they communicate with the mesh network. This in here, I made this face when I opened this thing up, is basically an SSD drive that contains a full Windows operating system on the thing and all the software that runs this. My mind was blown basically when I dumped this and made a copy of it and saw what was on it that we'll see shortly. This is just an Intel motherboard. I mean, it's running just a full-on computer inside here. And it has a cellular modem that's there in the bottom corner, which is how it relays all this information back to the power company. And so the whole software, this collector software, is all written in .NET. So anybody that's familiar with .NET knows you can open it up in a disassembler here, and it shows you basically all the source code, just everything, all the details of how it's running, what it's doing, and all that. And you can actually run it in debug mode and just step through all the code and add breakpoints and experiment with it. And so I hooked this up to one of these modem boards over a serial port that I connected into the computer, and it communicates with the thing, and it fully runs. And so there was a configuration file that was in here. You see it here, and it looks like a jumbled mess. And so I was trying to figure out how to change settings, and I noticed in this .NET code that there's an encryption and decryption for it. So I just turned that off and told it to save the file with no encryption. Now I can change all the settings that are in there and configure the network any way I want. And so with that, this simulated environment talking to a meter in this Faraday cage was able to communicate with it. And it joins my own personal network that consists of one smart meter and a couple light bulbs that I'm measuring the power of. And so using this, I can now run a lot more interesting experiments. And so this has not been released anywhere. I'm basically releasing as part of this talk. This is a transmitter that I'm building. And so this device, it's right behind me, you can't see it. It's transmitting out. It's also listening to itself through the other port, and it's going to one of these Landis and Gear modems. And that modem right here is also connected to the computer over that serial connection you see there. And I have it in a special test mode. And in that test mode, it lets me pick different channels I want to listen to out of this 260 and see if it's receiving data. And so I send burst transmissions, and this is a bit of the journey and the research I did to figure that out and how I was able to send these transmissions. So let's just kind of take a look at what it is we're going to see here. So if we think of a graph here with time on one axis and the frequency that the meters transmit in on the other axis between 902 and 928, these meters are just jumping all over the place all the time within this range, sending things. And they're also listening at a bunch of different channels that we don't know about, because you can't tell when it's listening. You can only tell when it's transmitting. And so what we're going to do, if we look at frequency down here instead of time, and we just look at frequency against power, you'll see on a lot of the things and these other ones we've seen, basically bursts of energy at different frequencies. And so all these different frequencies are its kind of ranges of spots that it can transmit, and also spots that it can listen. So there's 260 different channels, like I've said, that it could potentially listen on. And so at any given time, every 7/10 of a second, it jumps channel to channel to channel to channel. So how do you send a message to it and know that it can receive it? My idea was, what if I could just transmit on all 260 channels simultaneously, so no matter where it is, it has to deal with the message that I send it, and I don't have to figure out anything about this frequency hopping pattern. So that's the journey that I started to take here. And so I started to build different transmitters. I've only ever been able to transmit on one channel at a time, but I thought, how could I do it on multiples? So I put these 4 blocks here. They basically just send a little signal, a cosine wave in this case, into this block that basically puts them all together and puts them on a wider channel. So that instead of being individual signals on individual channels, it groups them all together. And that's what you see here. And so it's a very basic simulation for me to say, hey, do I think this could work? Like, is this a viable solution? And so I set those cosine waves at different frequencies, and I see those different frequencies come through here. And I said, all right, that looks like probably this could work. So I said, well, maybe how about 10? So I feed 10 signals into here, into this block, and aggregate it, still just running a simulation, no actual hardware or anything, but I see those 10 signals come across. They're all spaced 100 kilohertz apart. That's how the meters are spaced. 902.1, 902.2, 902.3. That's how they all are from 902 to 928. And so since that worked, I thought, okay, maybe I can modulate some data. So I'm going to send in some random noise, but I'm going to modulate it, which is that kind of crazy looking little signal we see there. And that is basically just random data being sent across. And I said, okay, well, I can send random data and keep it in a channel. So that's good. Can I do that with multiple channels? So, and I didn't want to use random data. I need to verify it. So I took some data here, some ones and zeros, and I put it together and I sent it through 3 channels into this block, still running a simulation. And I built a little kind of decoder to show it on the screen so I can say, hey, there's my little ones and zeros, and I'm listening to this channel. Let me tune it to the next channel. So I slide this little slider over, and you see kind of what would be static if you were tuning an old school radio or something. And I get to the next channel, and sure enough, there's my data. I slide it over, and I get to the next channel, and sure enough, there's the data. I say, okay, great. So I can send some data across 3 different channels here and pick it up. And the channels next to it don't interfere or anything like that. So now I need to send some actual kind of data, not just test data, and I need to do it with hardware. And so this flow graph at the top is basically 512 bits, ones and zeros, that are an actual smart meter packet for this test network that I have behind me, that I send out of a software-defined radio, transmitted, and it's wired into a modem. So it's transmitting it, but it's over a closed connection. So it's not transmitting it out in the air. It's just transmitting it directly between the device and the modem. And then I also listen to it with this piece. So I kind of feed back into the radio and listen and say, okay, what am I sending? And I'll show it on the screen so we can see it here. So if we run that flow graph, there's the data at the top. You can see it's much more complex looking than my other little ones and zeros. And here's that one little peak of information. So on one single channel, I'm sending that burst of energy every half a second or so. And so this little terminal window we see on the top left here, that's connected into the Landis and Gear modem. And what I'm going to do is go to the channel that's transmitting on. It's 915.1 megahertz, which is channel 131. So I'll tune to channel 131, and then I'll start the receiver. And when I start the receiver, we'll see this message. Here it comes. Every half a second, that message is popping up, and that's great. It says it was able to receive it. It says it's good. I can see that it's the data that I'm intending to send. There's the CRC that's right on the end, this 9E30. And so we'll see that in the other messages that I send because all I'm doing is sending the same message. Now, if I change to any other channel, though, out of between 1 and 259, it doesn't receive anything. So all I'm doing is sitting on this one channel. If any meter happened to jump by and land on the channel I'm on, well, it would hear my message. But it's not going to hear it all the time because it's jumping around all over the place. So what I need to do is scale this up, obviously, so that I'm sending on more than one channel at a time. And so if we go back to the flow graph here, what we're going to do is go to this next one. And so I do a similar thing to what we saw with the simulated data. I take this packet of information that's up top here, and I put it into this block, which is going to basically multiply it out and put it on 10 channels at the same time. So that when I start this flow graph, we won't just see one little burst, but we'll see 10 bursts all grouped together. And that's what this is down here. So they're not spaced out appropriately right now. They're not spaced at exactly 100 kilohertz. I have to do something to change that. But I do send 10 bursts of information all at the same time. So now we go to this next flow graph. At this point, I'm super happy. I'm sending out more than one transmission at a time. It's probably super late at night while I'm working on this. And I throw this block on here, and this block spaces my channels out appropriately. And I'm feeling pretty good. So I go down to the row below that and I say, hey, instead of 10 transmissions, let's send 20 at the same time. So I send this block of 10 into this one down here, that multiplies it up by 2 so that instead of 10 transmissions, it's 20. And then it goes down again to the bottom where the hardware is. And so now we see, hey, there's 20 bursts of information, and I'm sending it once a second. So let's go back to our channel here, 131, and we say, hey, there's the information. It's coming across. That's awesome. But also, if we change to another channel now it's also coming across as we go up or down around that channel 131, which means now if a meter lands anywhere within these 20 frequencies, now it's also going to receive the message. So now the game is, how do we scale this up? How do we go up from 20 to 40? So you see down there, the block at the bottom now is 40 that we're going to send out. and I do that a little bit, and then we go up to 80, and I take the 10, I multiply it up to 80, but I start to have a problem. It's a little disheartening at this point. When I send the data, I start getting these things called underflows. They're these little U's that show on the screen, and what it means is that the data is not being processed fast enough through that flow graph to get to that software defined radio that's transmitting it in time. And so what that translates to is that I'll still receive some data, but it's intermittent. Like it's not going at exactly once a second. Sometimes I get some transmissions and they come through once a second. Sometimes it pauses for a while. And so it's starting to become unreliable. And we're not even at 80, we're only at 80 transmissions at this point. So we want to scale it up beyond the 80 and go up to 260, which is what this is. But when we start and we run this flow graph, what we see is that now nothing happens. So as it starts to transmit, it's just a massive wall of underflows. Nothing ever makes it through this thing out to the modem. And so at this point, I'm trying to figure out what is going on with this thing. And what I realize is there seems to be some weird relation between multiplying it up by 10 and then multiplying it up by 260. And so this was real late at night, I decided to make this epic flow graph. And this thing is literally 260 inputs to one output. And so I run this thing, I slowly scaled it up about 30 at a time. And you can see it sends like that's 260 channels of information that it's bursting out. I'm still getting these underflows, but it is kind of working. But we're back to this intermittent problem. So how am I going to have something that I know will be sending the transmission every time? Like, when I want to talk back to these, it has to be more reliable than what this is. So I go to sleep and I wake up the next morning and somebody in this chat channel I'm in had an amazing idea, and it was to use a completely different block that's way less processor intensive. And when I did this, holy cow, it worked perfect. Like you can see the transmission at the bottom looks super clean, all those channels, and literally any channel I set this modem to now, between 1 and 260, it perfectly receives a signal every single time. And so now what I have is a receiver where I can receive any information from any channel that it's being transmitted, and a transmitter where I can transmit back on every single channel. And so I can now build my own transmitter receiver to talk to these smart meters and figure out, can I do some kind of network attacks on them? Can I create broadcast storms, all your traditional IP kind of attacks? Can we do this, but on the wireless mesh network side? And so that is going to be the basis for all the future attacks that come up after this that I'll work on. Now, a lot of this information, I have a YouTube channel. I post it on there. You can go there. It's like a choose your own adventure at this point. You're with me right now. This is as far as I've gotten. I don't know what's coming next. I have a website where I link stuff off to so you can easily find it, and a wiki where I try to post all this information. You can create a free account there. Anybody can create an account, post anything you're working on, or contribute to this smart meter research yourself. It's kind of a game that we can all play, listening in and seeing how they work. And so, I really appreciate you taking the time to watch this. So you can find all this information posted on my GitHub. The most recent stuff hasn't been uploaded yet, but it will be up there soon, just because this research is happening in real time. So thanks a lot for watching. You can find my stuff on the Richessum website. You can also find me on YouTube and Twitter and all these other places. And I look forward to hearing your comments and feedback and setting the direction for this research. It's a kind of choose your own adventure game, and we're all on this ride together. Thanks a lot.